Hi, my name is Zheda. I'm a first year PhD student at the Ohio State University, and today I want to present our paper Visual Query Tuning towards effective usage of intermediate representations from parameter and memory efficient transfer learning. So in this paper, we propose visual query tuning, a simple but effective approach to leverage intermediate features of vision transformer for transfer learning. And by introducing learnable query tokens, we could summarize rich intermediate features without changing those features. And the prediction hub will leverage the summary of these features for more accurate predictions. And VQT is a parameter, memory, and training efficient methods, and is also complementary to other parameter efficient fine-tuning methods. By combining VQT with other fine-tuning methods, we can unleash the power of transfer learning. So in computer visions, for a very long time, the dominant architecture was CNN, convolutional neural networks. However, the situation has changed a bit since 2021, when Transformer began to demonstrate very strong performance for many computer vision tasks. And the computer vision field is embracing this transformer-based architecture. Similar with the large transformer models in the NLP field, the number of parameters of transformer-based vision model also grow rapidly. So in order to use those models, the pre-training and fine-tuning paradigm has been widely adopted in various fields to achieve good performance for the downstream task. And the common way to do this is to pre-train a very large model with a huge amount of data to obtain a foundation model, and then we fine-tune this foundation model to adapt to different downstream tasks. Generally speaking, there are two ways to fine-tune a large model. Full fine-tuning updates all the parameters for each downstream task, and although it often has a good performance, it requires very high training cost and time. Moreover, you need to store a separate fine-tuning model for each task, making it very efficient. And this problem becomes more salient with the transformer-based model, whose parameters grow exponentially. And on the contrary, linear programming only trains and stores new prediction heads to recombine features while keeping the backbone frozen. But despite its computational and parameter efficiency, linear programming is often less attractive due to its inferior performance. And several recent work have attempted to overcome such a dilemma in transfer learning. And one representative work is called Head to Toe, which is published in ICML 2022. And by allowing linear programming to access the intermediate features in the network, Head to Toe can improve the performance of linear programming while keeping low training and storage costs. However, given numerous intermediate features in the network, most methods require pooling to reduce the dimensionality, which would eliminate some useful information before the prediction head can access it. So, to efficiently and effectively utilize intermediate features, we propose visual query tuning, a parameter and memory efficient transfer learning method for transformer-based architectures. And before we discuss the detailed VQT, I want to introduce the notation in this paper. We use the pink and blue color to represent tunable and frozen parameters, and the dashed rectangle shows the intermediate features. And if they're not modified during the tuning, we use the transparent rectangles to represent them. And if they are modified, we use the gray rectangle. So this is a linear programming, as we can see, where only the prediction head is tunable during the fine-tuning, and all the intermediate features are not modified. So compared with linear programming, VQT introduced a handful of learnable query tokens to each layer. So through the multi-head self-attention, these added tokens can then summarize the intermediate features and store them into the output. Then the prediction head will leverage the summary of intermediate features from each encoder for the final predictions. So as shown in this figure, every time we could insert some additional tokens as inputs for each encoder, these tokens don't change the output of the original inputs, same as the linear programming. But for people who are familiar with self-attention, we know that for a specific token, such as the green token here, the self-attention basically will calculate the relatedness of this token with other tokens. And if we add more tokens, this added token definitely will change the output of this green token. But however, in VQT, we found that all of the intermediate features are not modified. So why the added parameters do not modify the output of the original input in VQT? So in order to answer this question, we need to understand the mechanism inside VQT. So this is the KQV module in a pre-trained model. If we treat the added tokens the same as the other input tokens, this is basically a recently proposed method called VPT, where the added tokens are used for value, key, and query. And with this mechanism, the output of the original inputs will be modified with the self-attention module. And this is also the goal of VPT, which aims to adapt the intermediate features. But on the contrary, VQT only uses the added tokens for query. Therefore, the intermediate features are not modified because the value and key vectors are not changed at all. So in fact, VPT and VQT takes fundamentally two different routes to approach transfer learning. VQT learns to select which intermediate features are more useful for the downstream task, while the VPT aims to adapt the intermediate features for the downstream task. And because of the mechanism VQT, it has several attractive advantages. Firstly, its parameter efficiency. VQT only tune and store around 1.2% of the total parameters for each task. Secondly, because it does not change the intermediate features, it does not need to run a full backpropagation through the backbone, and therefore it saves more than 70% of the training memory consumption. Moreover, since the intermediate feature not changed, we only need to compute the intermediate feature once in the first epoch and then reuse them in the later epochs, making them very training efficient. Lastly, most of the parameter efficient transfer learning methods focus on how to adapt the intermediate features, such as VPT, while VQT focuses on leveraging intermediate features, making it complementary to most existing methods. In terms of performance, VQT outperformed head-to-tail, which also leveraged intermediate features in 16/19 tasks in the VTAP1K dataset. It also surpassed the full fine-tuning by 2.1%. Remember, full fine-tuning requires tuning the whole network, while VQT only tunes around 1.2% of the parameters. As we mentioned before, VQT and other parameter efficient tuning methods are complementary and mutually beneficial. Here we combine VQT with two state-of-the-art methods, VPT and a deformer, on three different types of backbones. As we can see here, when it combined with VQT, this method gets pretty significant improvement in most cases across different backbones and data groups. Moreover, when memory is a constraint, VPT and a deformer experience drastic performance drop. But thanks to VQT's query-only mechanism, it shows very strong performance under memory constraints. So, to sum up, we introduced visual query tuning, which is a very simple but very effective approach to leverage intermediate features for transfer learning. And by introducing some learnable query tokens, VQT can summarize intermediate features from different layers, but without changing those features for more accurate predictions. VQT is a very parameter, memory, and training efficient method, and is also complementary to other parameter efficient fine-tuning methods. Thank you so much for listening. If you have any question, please don't hesitate to contact us. And we also want to thank NSF, Cisco Research, and Ohio Supercomputer Center for supporting our research. We also want to thank our collaborator at OSU and Cornell. Thank you.